Okay, this topic for today is the slope of a parametric curve, and I'm hoping this will help us for our class on Thursday. As we get a little bit more pressed for time, I was hoping this would help somewhat the lesson on Thursday. So anyway, let's talk about the main topics for this section. So extending from the idea of, what a parametric curve is, and basically what we did on last Thursday was we sketched a parametric curve and we eliminated the variable. And what we're going to do today is actually find the derivative of a parametric curve, and a main lead out from that will be finding the slope of the parametric curve. So definition wise, how do we define the derivative of a parametric curve? Well, we will take a curve C, a smooth curve C, and this curve C is defined by the parametric equations. X is f of t and y is g of t. So what we're going to do is define the slope of such a curve defined by these two parametric equations, and that derivative would be dy dx would equal dy dt divided by dx dt, where of course my denominator has to be non-zero. So that derivative of x with respect to t cannot be zero. If that happens, then we got major problems and we won't have a derivative of this particular parametric curve. So let's look real briefly at the derivation of this derivative. And the way I'm going to present this is, okay, let's say we have a curve on a plane, and we want to actually measure the slope between 2 points. That's how we're going to think the derivative again. Well, what we would have to do is have our parameter t, and the distance that we travel down the x-axis would be delta t, which would give my new coordinate t plus delta t. But see, that allows us, much in the same way that we define the ordinary derivative as the slope between 2 points. We have now, by taking a parameter and adding a distance to the parameter, we've created 2 points in which we can find the slope of the tangent line between the curves. And these coordinates would be f of t, comma, g of t, because remember, it's a parametric curve. And then the other one would, now using t plus delta t as your actual plug-in value, it's going to be f of t plus delta t, and then f or g of t plus delta t. So my slope would be, and I'll go away from this for just a second. My slope would be basically subtracting y coordinates. We would get g of t plus delta t minus g of t over f of t plus delta t minus f of t. So that's sort of how I get to start out. If we look at the next slide, that's how I get g of t plus delta t minus g of t over f of t plus delta t minus f of t, kind of like a difference quotients for parametric curves in a sense. So let's get the derivative from that. So really the way we're going to want to define our slope is to go ahead and take the limit as delta t approaches 0 to get that distance between the 2 points as close together as possible of this g of t plus delta t minus g of t over f of t plus delta t minus f of t. And if we, as you can see in the PowerPoint, if we divide top and bottom by delta t, that would not change the value of the fraction. We would then get g of t plus delta t minus g of t all over delta t, and the same thing in the bottom, but f of delta t, t plus delta t minus f of t over delta t again. And if I split up the limit at that point, and you can see in this next step, if I apply the limit to both top and bottom, I'll get, the limit on the top, and I'll recopy that quotient. And then on the bottom, this now will become basically the derivative. It's g prime of t over f prime of t, or dy dt over dx dt. So again, let me see if I can get this all in here. And I'll stop this. I'll kind of go to this, actually, the camera for a second. So using these 2 points on the curve, we can set it up as the limit of this difference using the slope formula. That will simplify to get the derivative of both g and f, and we're done. We get this dy dt over dx dt. Okay. So next question. Let's basically go to an example. Now, in a lot of these, I'm not going to pause as much in between problems because I want to shorten the length of the video. And I figure if you want to pause and write something down or review what I just did, you could just do that. Once I'm done with the problem, you can pause it, get down what extra information you might need, and then go on. So this will be kind of a little more rapid than class in terms of transition between problems. Okay, so our first example applying this will be for the parametric curves. X is cosine t and y is sine t, and we're going to find dy dx. So on this one, I'm probably not going to go to the dot camera because these definitions are so basic. So I'm going to go straight to the solution. So all we have to do is take the derivative of y and x. And the derivative of sine t is this cosine t, and the derivative of cosine t is negative sine t. So basically, we have x as negative sine t, and y is, the derivative of y is cosine t. So dy dt and dx dt. Well, if we use the formula, dy dx is dy dt divided by dy dx dt, we get negative cosine divided by sine, which, of course, cosine divided by sine is cotangent. So the end result would be negative cotangent t would be my parametric derivative of the first example, which my parameters were cosine t and sine t. All right, so like I said, I will, again, you do have a chance here to pause it. I'm going to go to the next one, and you can kind of just get, control it on your own speed in between problems. And of course, I can answer any questions you might have about this particular video or set of notes. So on number 2, I'm going to let x be cosine squared t and y be sine squared t. Now I am going to go to dot camera on this one because this one, the derivatives are a little bit trickier, not super tricky, but a little bit trickier than the last problem. And again, we're still finding the derivative dy dt, or dy dx is what we're looking for. So the trick to doing these two derivatives is basically to write them as quantities. So if I rewrite this as cosine t squared, like that, as a quantity squared, and the same here, what this does is allows us to use the chain rule, because the most convenient way to do both of these derivatives is using the chain rule. So recall how the chain rule works. Dy dx dt would be, use the power rule on the outside. So it'd be 2 times cosine t to now what will be now the first, and then times by the derivative of the inside, which in this case is negative sine t, is the derivative of cosine t. And if I clean this up, I'll end up getting negative, because I have the negative in front, 2 cosine t, because again, the exponent's 1 sine t. So dy dt, I'm almost going to mirror what I did here, except my inside now is sine t. So I'm going to go 2 times the front, so 2 times sine t, and I'm not going to worry about the exponents. This is going to be first power again, times the derivative of the inside, which is cosine t. And really, I'm done. And that's basically the hardest part of this example. I now have the 2 derivatives via chain rule, which are negative 2 cosine t sine t. It's reversed in this PowerPoint, but don't worry, it works out the same. And then dy dt is 2 sine t cosine t. Well, if I write these, getting my derivative as that quotient, I'm just going to take basically 2 sine t cosine t divided by the bottom, which is negative 2 sine t cosine t. And I did switch the sine and cosine there just to make it easier. And 2's cancel, sine t's cancel, cosines cancel. And look at that, we just get negative 1 as our derivative with those 2 parametric equations. Okay, so again, I will pause for just a second to allow a little lag in the video, maybe 2 or 3 seconds where you can pause it. And I will go on to example 3. Don't worry about I am not going to cover second derivative, the parametric derivative, second parametric derivative. So I'm just going to stick with slope and arc length, as you'll see in a minute. So number 3, our 2 functions are x is the square root of t, and y is 3t minus 1. And I might be able just to keep this up here while I bring up the slide. So I'm going to just do that. So there you will have the solution to the right. But these derivatives, are, again, are fairly basic. I mean, the derivative of 3t is just 3. And of course, the 1 drops out. So, I mean, there's not much to that one. This one is fairly basic, but you do have to switch t to the 1/2 power. And your derivative of t to the 1/2 power, well, if you do the power rule, it's going to be 1/2 times t to the negative 1/2, basically, when you take away 1 from the exponent. So now I have 1/2 and I'll have t to the negative 1/2. I didn't want to make that half so big. I thought I was going to have to move it down. So I think I'll just leave it like that. And in fact, you'll see that I did not switch it back to a positive exponent because we got to plug it in the formula. And it's actually easier just to keep it as a fractional exponent and then switch it later. So if I do my actual derivative, dy dx, it's going to be dy dt, which is 3 divided by 1/2 t to the negative 1/2. And that simplifies to, recall, if you have 3 divided by half, that's actually 6, because you're literally taking 3 times the reciprocal of the bottom, which is 2, so that gives you 6. So you end up getting 6. And if you just move the t to the 1/2 to the top, it now is a positive exponent. And we can switch it back to a square root. So we actually end up with our derivative is 6 times the square root of t, as you can see. And then my slope would be 6 times the square. If I plug my parameter is t equals 1, if you go back to the original problem, it says that it's at t equals negative 1. So if I plug in negative 1, the square root of 1 is 1. And my parameter has a slope of 6 at that point. At that parameter value, t equals 1. So again, we're done, and our derivative again turned out to be. I'll summarize this real quick. But my individual derivatives for dy dt and dx dt were t to the 1/2, t to the 1/2, and 3. My actual parametric derivative was 6 times the square root of t, and my actual slope of the curve was 6. Okay, example 4. Now I got all kinds of stuff I need to change there. Let me get the paper here. All right. Find the slope at theta equals pi over 2. And your two parametric equations are x is cosine theta and y is sine theta. So I'm actually going to just kind of run through the PowerPoint here because, again, these derivatives are so simple. I don't really think you need to see me do the math by hand in this particular problem. It's just basically definitions. So as you would imagine, the derivative of y, d theta is cosine theta. Now, do notice that I have to keep my parameter as theta. So now I'm writing it as dy d theta and dx d theta. So that is important to note that. And actually, I might just go ahead. Let me pull up. I got a printout here. I can make reference to. So again, that is one thing to keep in mind is now our parameters are our parametric derivatives are dy d theta and dx d theta, which again, just basic definitions. Derivative of sine is cosine. Derivative of cosine is negative sine. In this class, as you know, we always got to keep track of what direction we're going. So we're doing derivative, not antiderivative. And then my basic parametric derivative after I do my dy dt and my dx dt is dy dx, which is cosine. divided by negative sine theta, which again, sine divided by cosine is cotangent. So we do actually get that the derivative is negative cotangent theta. And then plugging in our parameter of theta equals pi over 4, it turns out that cotangent of pi over 4 is 1. Let me see if I still have my unit circle. I do on my phone. Here, just for a second. If you go to, if I can find a place where I don't have so much glare, I think that's good enough. You can kind of read it. But at pi over 4, look what happens. Both sine and cosine are square root of 2 over 2. So, I mean, that's basically going to divide out and be 1. And of course, you do have the negative in front. So the actual final answer for the derivative is -1. That's the slope of your tangent line to your parametric curve. Okay, want to mention a couple things here. This one more topic and 2 examples. Let me go through these. And the last topic is arc length. So if you have a smooth curve again, and they just describe it as C. But what C is basically, it's a set of ordered pairs that are basically f of t, g of t again. So x and y are defined as these parametric equations. And hopefully you're kind of getting used to that. We physically did that in class on Thursday. We did a chart. We took each parametric equation, plugged those values for t, and then solved that, how that generated a set of points. And we graphed this set of points from there. And that gave our parametric curve. So this is based on that concept. So we defined the derivative of a parameter of like a set of parametric equations, slope that results from that. And now we're going to look at arc length. So our parametric, we get a nicer result actually for the parametric equation, or for parametric equations in defining arc length, because what happens is we get this nice definition that basically is the integral from a to b is my arc length of the square root of basically dx dt squared plus dy dt quantity squared dt. And that will give us our arc length formula. So I'm going to do 2 examples, one where we just set it up and then one where we set up and actually solve it. So example 5, and I switched the order of problems a little bit from what's on Canvas, and I'll try to re-upload those. It's not a huge difference, but I just thought it would have a better flow. If we did a video, it would just be the first 6 examples. I think that would be enough to get us a good start on arc length, and then I can kind of fill in the blanks again, like I said on Thursday. So it says write the integral that represents the arc length of a curve. Do not solve the integral. So we're going to set this up, and that's it. So I think I'll just go to my sheet here, and I will go ahead and just get my derivatives. And maybe I should write the equations down. So x is natural log t, y is t plus 1. And these derivatives are very simple because using basic definition of ln t, its derivative is 1 over t. And derivative of t plus 1, that's the easiest derivative we've taken in a long time. It's 1. So my arc length L will be the integral from 1 to 3 of the square root. And then I'm going to square my 2 differentials, which are 1 over t and then 1 squared t. And then, of course, we do take the square root. I probably can go ahead and work out the quantity squared. So that basically will be 1 over t squared plus 1. You could even go to this form, because you could think of it as t squared over t squared. So if you wanted to combine it into one fraction, it would look like this. It would be the square root of, I'm going to go and switch the terms around. It's going to be t squared plus 1 over t squared dt. I did switch the order, but in any event, I would, either form probably would be fine if I can get my dot camera to work. So things just don't change for me, whether I'm doing a Zoom or lecture or YouTube video. I always get the dot camera messed up, so that's me to T. All right, so back to the share. And I only took it to the, this step. So like I said, it really, you could play around with forms. I'm not going to be really that picky. If you understand that you're taking your two derivatives of your parametrics and using this formula, in my mind, you understand the concept. This could integrate. I could throw it out as a challenge. I don't want to fool with it now because I'm afraid I would spend 15 minutes and it could get ugly. It might take a while to figure it out, but it's possible this could be solved by trig substitution. I haven't played with it, but that's possible. All right, going to number 6. And again, we got a situation with two parametric equations, and we are defined on a domain from 0 to 1. And you're always going to be on some finite range finite domain, because chances are, if I ask you to do the arc length of a curve from negative infinity to infinity, it's probably going to be infinity. But anyway, unless there is some odd thing that happens that reduces down and it stops at some point. But if that curve is continuous and differentiable, it's probably going to be infinity. All right. So our two parameters are t squared and 2/3 t cubed. I think I'm going to have to use the whole sheet of paper for this. So I'll go ahead and get this copied down. I'm probably going to have to go dot camera to finish this out. So there's my two parametric curves. And of course, I'm going to run my integral. Will run from basically 0 to 1. Okay. So let's do the derivatives first, which would be dx dt would be 2t. And then dy dt, you're going to get 3t squared, or 2t squared, because 3 times 2/3 will result in 2. And then, of course, reducing the exponent by 1 gives me t squared. So let's set up this arc length. It's going to go from 0 to 1 of the square root of 2t squared plus 2t squared to the second power, dt. And let's expand this out. I'm actually going to find the length of this curve. There's my integral. I set it up, and that part's done. So I'm going to see if I can get this to integrate. So squaring 2t gives me 2t squared. Squaring 2t to the second power gives me 4t to the fourth. And of course, I have my dt term. Well, if you look at those two terms, what you're seeing here is you do have a common factor of 4t squared. So let's see what happens if I factor that out. So I'm just going to take the inside of the square root and factor out 4t squared, which will leave me 1 plus, and then this would, of course, pulling out 4t squared, leaves me only with t squared. Well, that works out well because now we can take the 4t squared out of the radical because you can take the square root of 4t squared, which is 2t. So now I have 2t times the square root of 1 plus t squared. And notice we have that situation where outside's the degree higher, degree less than the inside. Looks like u sub the me. And if we do make u t 1 plus t squared, the derivative would be 2t. So this looks really good for u substitution. So let's try it. So picking, I'm going to have to write it down below. I just don't have any more room. If u is 1 plus t squared, du will be 2t dt, and that seems to work almost perfect. Because now we can perform u substitution. I'm going to have to take those. Hopefully you guys at this point have the two derivatives. I just need more space. All right. I'm going to leave the blanks. I'm going to leave the limits blank for a second because I can adjust them. I can change the limits. So 2t dt will end up being your du. And 1 plus t squared is my u. So now I have square root of u du, which will integrate very easily. My limits do have to change. I'll write to the side here. But I mean, basically, if I put 1 in here, 1 squared is 1 plus 1. It's just going to change from 2. And then my lower limit, putting in 0, 2 times 0 is just, or excuse me, not, I had the wrong one. It's actually 1. If I put 0 in, I get u as 1. So I can, that's an easy change of limits. It goes from 0 to 1, from 1 to 2, based on this u substitution. Then I can basically make it u to the 1/2. And the antiderivative of u to the 1/2, if we add 1, it's u to the 3/2. And of course, we can flip that over and times it by the front. So it's 2/3 u to the 3/2 from 1 to 2. And then that will give me 2/3 times, and plugging in 2 and 1, I'm going to get 2 to the 3/2 minus 2/3. I'll put parentheses in there so it looks like we're timesing. 1 to the 3/2, which that's basically 2 times, and this will be basically, if we cube 2, it's 8, and we take the square root of 8, it reduces to 2 square roots of 2, and I'm going to factor that out, and then I'll factor out the 1. So I basically just, if I take the 2/3 out, I get 2/3 times, and this again, 2 to the 3/2 is 2 roots of 2, and then 1 to any power is 1. And then going back to my solution, I didn't actually write this step in there, but as you can see, I got the same thing. I changed, u substitution, and then changed my limits. If you want to convert this to decimal form, it's going to basically come out to about 1.21 would work as well. So I probably, even if you gave me this, that would be fine. There's always that factor with WebAssign. And of course, this is going to go on the test 3 anyway, not this current test. But often in a situation like this, WebAssign will give you a hint, though. They'll say they want it in, they'll say round, give me a decimal form, round it, or put it in a square root form or whatever. So, and I can kind of be flexible on that too. I can pretty much tell like if you entered in the decimal form and it counted it wrong, I could tell that by just what you're entering in. So chances are that I wouldn't lose sleep over that, because either you'll probably be able to figure out what they want, or I'll be able to adjust it, one of the two. So don't spend time and energy in this course that way. Just focus on learning the material. Okay, so that's the arc length of those two parametric curves on the interval from basically 0 to 1. And I'm probably going to stop the video here because I'm sure I'm getting long in length here. I try to keep my YouTube videos under a half hour. But anyway, you can go back through this video. There's 6 examples. There's 2 arc length, 2 slope with the derivative application, and 2 derivative problems. And then your basic definitions are in there too. So I'll be open the floor to any questions, actually opening the Zoom room on Thursday up to any questions on this. And we'll transition from here. I mean, this really is basically the whole section when I covered. Really nothing different than I'm going to cover out of than what we did. So if I can wrap things up pretty quickly, I probably will go on to polar coordinates on Thursday. But again, if I have to go back and reconstruct some of these problems, that's okay, and answer questions. I think I can figure out a way to bring this in. So anyway, I'm going to keep this video idea open, because if we do get desperate for time, that might be a way I can kind of get you guys through this material. Because you got to remember, I'm sure a lot of you are going on to Calc 3, and they're just not going to, they're going to pick up basically in chapter 11. So I want you guys to be ready as well. Okay, that's all I have. So enjoy your election day off. If you have an interest, go out and vote. I really encourage you to do that. And I think that's all I have. So enjoy your afternoon or evening or morning, or at 3 o'clock in the morning, whenever you choose to watch this video. And I'll see you guys in class next time. Until then, stay safe.